textbook at your desk, open to page 299. And we are getting into the quantitative part of the course. Part of the course, and we're starting with the definition. And the definition is probability success over total. Odds are not an AP topic, but I'm just showing you that odds have a different definition. And odds are failure to success. So you notice what's going on here. One of these is being left out in each definition. So in probability, failure is not part of the definition, and in odds, total's not part of it. But it's a mistake to use probability and odds interchangeably. Does that make sense? So if the probability, God bless you, if the probability of you, think about this, rolling a 1 on a die. You're trying to roll a 1. It's a fair die. You roll the die. What's the probability you get a 1? It's not a trick question. The probability of getting a 1 is 1/6. Yes? What about the odds? What would the odds be? 5 to 1. Okay? We talk about odds against. We don't say odds for. I mean, it doesn't make sense. So if you read something in terms of wagering, it's going to be failure to success. So the odds of you rolling a 1 would be 5 to 1. Against. Well, think about that. It's 5 to 1. So you should get paid in that ratio in order for you to break even.
So I feel like horse racing and stuff, when they give odds,
Yes.
like 3 to 2 odds.
Yes.
So that would be like if they ran the race 5 times, they would lose 3 and win 10.
Yes. That's exactly right. That's what it means. So, the issue with that, Sean, is that not too many people are interested in horse racing anymore. It used to be a big deal. Okay? I'm interested in it. And if you see those, the thing that's fascinating, if you go to the track with your family, those odds change. It just instantaneously. They're changing as people bet on these horses. And the track builds in some money as a profit, but then this is being determined by how people bet on the horse. And Sean is saying, if you see a 3 to 2, well, if it's 3 to 2, that's going to be the favorite. Does that make sense? If it's 3 to 2, that means that that horse would be expected to win 2 out of every 5 races against the same horses. Okay? So, on page 299 and 300, they talk about flipping a coin.
If you have like half a number, do they just double it? So that it's like 2 even numbers, 2 whole numbers. Like so it's not 1.5 to 1. It's
Correct.
2.
That's what you'll see. Like it means the same thing. You could reduce it. See, we write this as a ratio instead of a fraction, not to mix them up, but you can think of it the same way.
So if you have something like 1 to 0 odds,
There's no such thing as one.
or 0 to 1, I guess, like where it's definitely going to happen.
0 to 1, yeah, if something has to happen, the probability is 1. Well, there's, you don't speak of odds of something that's definitely going to happen. The probability is 1, it's a certainty, okay? So now what? On page 300, they have this activity about flipping a coin. And if you have a fair coin, what's going to happen? And there's a picture in the book that refers to the law of large numbers. And what they mean by that is, as the sample size gets larger, the variability goes down. And you could have, take a look at this. Here's the first 10 tosses of the coin. We good? This is a picture in your book on page 301. And this is the probability of getting heads. What happened on the first toss of the coin? It
It's heads.
was heads. Yes?
What did you say right after you said law of large numbers?
Well, this graph is going to demonstrate the law of large numbers, okay? That as the sample size goes up, the variability will go down. So, the first toss here was a heads. How about the second toss?
Tails.
Tails. Yes? Because you can see what happened was, as you go to the right for 2, now you get a 1/2 chance. Yes? The third toss, heads. Fourth toss, tails. Fifth toss, tails. Yes? And then that's for 10 tosses. And the picture on the right's for 500. Now, it's the same graph, except 1 to 10 is squeezed way in over here. So you have to zoom in. But the behavior's the same. And they're saying, look what happens. You've got this variability about the expected outcome, which will be a half. And as you go to the right, that graph is going to that line. That's what the expected outcome is. So the point being, you could have a lot of variability in a small sample size, but over many, many repetitions, that variability is going to go down. And this is why your mistaken idea about when in doubt on multiple choice, pick C is so foolish. Because you have a very small sample size. Your assessment would be a small sample size. And after tens of thousands of assessments, yeah, the distribution of answers should be about even from A to D or A to E, depending on how many choices. But on one assessment, it's perfectly logical to have multiple C's in a row or multiple problems in a row where there is no C. Oh, you know what? There's a pattern here. This can't be right. It's time for a B. Baloney. The sample size is too small for you to make that judgment.
Would it make more sense to just like, not necessarily C, but for like a test that you don't, like if you're just filling bowls at the end, like just to pick one letter the whole way through?
No.
But then you're guaranteed that like one of them is going to be that one.
You're not guaranteed anything. Ready? Do you understand? Here's the question. I run out of time.
You're guaranteed there is an answer.
You're guaranteed there's an answer. That's just not leaving it blank.
But say you pick like A and then C
Yes.
and B, and like you don't know, like all those could be wrong. But if you just pick like straight through B, then like
Exactly the same
you would
likelihood.
think one of them.
Exactly the same likelihood. Let's pretend you run out of time in May, and you finished question 35. There's 40 multiple choice questions. Are we good? So we got this. We have 36, 37, 38, 39, and 40, and you know the time is up. And there's 4 choices. Are we good? So you're just going to randomly guess, which is not a good strategy because we'll coach you up in the spring that you should give yourself time to read all of them, not run out of time without even reading the question. But if this were to happen, okay, you have to understand this. Picking A is no more effective than randomly picking any other letter. What's the probability that you got 36 right? You just randomly guess. I remember?
25%.
The probability, 1/4. And what's the probability you got 36 and 37 right? 1/4 and 1/4, which equals 1/16. And you get all 5 of them right, would be 1/4 caret 5. That's it. No matter what, that's what you're going to get. No matter what letters you pick, it's not going to change. So for you to go A, B, C, D, back to B, it doesn't matter. And that's conceptually what this is about. Like for this is a fallacy for you to believe that there's some magic letter.
That's why you should try and read and eliminate some of the choices.
Correct. That's why what you're trying to do here in May is use Arathi's scrap paper method and say, I have to make sure I get a chance to read all the questions, not just in here, in any test. And then, if I don't know the answer, can I cross off answers that don't make sense and guess from what's left? Because if you can do that, then this would go down from 1 out of 4 to 1 out of 3, or even the best case scenario, 1 out of 2. But then it doesn't matter. 1 out of 2, well, should I pick C? That's one of the choices left. No reason to pick C other than other letters left. Should I pick all the same letter? No. If it makes you feel better about it, go ahead. There is no statistical support for what you're, like, staying with the same letter. Doesn't exist. Okay? So if you had large numbers, then you would expect something like in the multiple choice scenario to have a close proportion for each of the distributions of the numbers. But you get a small sample size. Look at this. Look at this variability compared to this. Now what happened here? The independent scale has been compressed, but the dependent scale hasn't. This goes from 0 to 1, 0 to 1. But because there's much more variability here, because you have a small sample size. And every assessment you take is a small sample size. So they did this simulation. Well, it's actually, this is a simulation. In 10 trials, you would expect to get heads half the time and tails half the time. All right? And then if you did 500 trials, you'd expect to get heads 250 times. So what happened? In the simulation, in the book, they got heads 3 times. Well, the sample size is really small. But when they did the simulation 500 times, they get a number very close to 250. So you're going to go to the theoretical value, the expected outcome, when the sample size goes up. So let's go here. Let's go to page 306 and read the bottom half of 306, which is a parking lottery. Okay? So what have you got? You've got 95 students. So we're going to take 2 digits for the simulation. So we're saying the students are 0, 1 through 95. And if we get 96, 97, 98, 99, or 00, we're going to ignore it. We're going to ignore 96 through, which essentially is 100. And we're going to ignore repeats. So success is that they're in the statistics class. So we're saying 1 to 28 is success. They're the kids in the class. And 29 to 95 are the other children that are not in that class. And you're going to pick 2 of them.
So like, if you like were to like change the placement of what, or change the numbers that the AP students were assigned,
Yes,
wouldn't that change the outcome of the lottery?
yes. That's why we're doing that's why you're doing a simulation. Like, you're going to do this hundreds of times. Like, you're just trying to understand what happens. If you were to do this hundreds of times, look at the distribution, then that would give you what, like, it's back up to what we said, the law of large numbers. Maggie's right. If you're just doing this by a lottery, and you pick a different row, you get a different outcome. Correct? But if you randomly pick it, then you would say it was fair. So this is not random, because you're just trying to see that we understand what we're doing. So you're looking at that row in purple on page 306. This is the way we would set it up. You can put the numbers, God bless you, in a different way, but it doesn't really make sense. Like you can start at 00, but why would you? Because it's way easier to keep track of the numbers, 1 to 28.
Is there any like meaning behind that table D, or is it just like a random like set of numbers?
It's supposed to be random.
So it's just like a table that the book generated to just.
Software generated, yep. So if you look into a different statistics textbook, like we have this book up here, they have a table of random digits. It'll be a different table.
So like the questions like would be able to be repeated in like other textbooks. It's not good. It's not good.
Well, ready? The only reason we're doing this is using that specific row is to see that everybody agrees with the answer so it makes sense. In reality, we don't want the answers to agree.
Okay.
We want it to be random. But in order, if everybody had a different answer, people wouldn't have confidence in what they did because everybody used a different row.
So even if a trial shows that they didn't get it, but if you repeat it over and over and over again, like they did for the simulation, it would show that 9% of the time they do both get it.
Yeah, well, you're getting to the answer, which we didn't get to yet. But yeah, the point is, it's back to this. It's back to right here. See, the probability, we're given, this is a fair coin. But you only flipped it 10 times. The simulation only gave you 3 heads. That's not wrong with the simulation. That's the variability you get with a small sample size. And if you keep repeating it, this number is going to go to half of the high denominator. But when you have a small sample size, there's variability. So you can't expect to get the theoretical outcome that you're expecting to have.
I'm still kind of confused. Why would we randomly assign the children numbers? Or like do them alphabetically? Why are the statistics in the first 28?
Because it doesn't matter, because the point is those numbers in the table are random. They're not random for this problem because they're given to you. But if you randomly picked a spot, yes, on table D in the back of the book, you randomly picked a row and a column, that's compensating for what you're suggesting.
Oh, okay.
You're right, because this thing right here, we said 1 to 28, and we're peaking, and the first 2 numbers are 70. But we wouldn't be peaking. We would be assigning the numbers first, then going to a random row and a random column in the back table, yes? And then seeing what happens.
So as long as you use a random row and a random column, you don't have to randomly assign the students or repeat it with the students labeled as different numbers?
Correct. You understand what Maggie's question is? It's misleading that you're looking here on page 306 and they already have that table there. That's only for the exercise. So
could you do the same thing but have your calculator generate the numbers?
Sure. Now, the problem with the calculator is it's based on that seed value, okay? So you would want to, technically I think you'd want to put in a new seed value every time you did it, but it's the same idea. And you're going to get, if you get a question, ready, there's a blurb on page 307. It says AM exam tip. On the AP Stat exam, you may be asked to describe how to perform a simulation. Well, you could perform it with your calculator. You could perform with a table of random digits. It goes to how thoroughly you explain it.
Okay, so how are the actual tables of random digits produced again?
So, 1 out of 10 chance this number comes up, and then just with replacement, generate the next number, Okay? So if you looked at that table, ready? There's 40 rows and, no, there's 40 columns and 50 rows. Yes? So there's 2,000 numbers there. You would expect 200 of each digit. You would expect that. If you had time on your hands, you literally counted them, you're not going to have 200 of each digit. Okay, you're going to have some variability. Okay? So, back here, this is the assembly, and they're going to pick 2 kids to get the parking pass for September. We good? And look what they got. You're on page 306. They got a 70. Child 70 is here. It's a failure in that they didn't pick an AP Stat child, but they found a kid. Then, the next pair of digits is a 70. Well, this is, the purple paper is with replacement. We're not putting that kid back in. They're not taking 2 spots. So we ignore the 70 the second time it comes up, and we get an 84. Good? So the first time you did this, you got 2 non-AP Stat children. Then what? The second trial, we're taking these numbers 2 at a time. Can you see where the 10 is? The break in the columns is only there to help you read it. The break in the columns has no significance. You step over that break. So you get a 10 and a 98. So you got 1 AP kid. Yes? Third time, 1 AP kid. So what are they telling you happened here? They did 100 trials. 100 trials. What did we do? 3. And in the 100 trial...
Why do we kill 98?
Oh, I'm sorry, 98 I should have ignored it. That's right. That's wrong. 98 should be ignored, not a 98 kid. So I'll have to fix that. Okay? So this kid, 98 gets ignored. Yes? And 55 slides in here. Then this is 18, who is an AP kid. And next to 18 is 19. So this would be 2 AP kids. So in 3 trials, very good. In 3 trials, we got 1 time where the 2 AP kids were together. In the book, they tell you they did it 100 times. And where we got 1 out of 3 times with their 2 AP kids, they got 9 out of 100. Yes? So basing it on the simulation where the sample size is 100, something that happens 9% of the time by chance alone, 9% or more by chance alone, is not considered to be significant. It's not considered to be statistically unlikely. So even though people say, oh, this thing is fixed because the 2 AP Stat kids got the parking spots, there's no evidence to back up what they're saying. People run their mouth all the time. Can you have statistical evidence to back up what you're saying? No.
So what percent would be like great? Like what percent would you have to get for it to be like actually?
Yeah, well, the Supreme Court has agreed to a cutoff of 5%. Something that happens 5% of the time or less by chance alone is considered statistically unlikely. But what if I'm right on the line? You don't have to worry about being on the line. Your line has no dimension.
I know, like, if you go like an infinite amount of times, it would for repeating a simulation, that it would show that probability. Is there like a specific number or like amount of times that you should, like a minimum you should do to repeat a trial?
Well, you don't have to worry about it because the software does it instantaneously. So we're not using the software in this room, but it doesn't matter when you dial that software, whether you pick 100 trials or 1,000, it'll do it within seconds. But, ready? Let's look at this thing theoretically. What is the probability? The theoretical probability that 2 AP Stat children got those parking spots? Do it on your calculator.